Welcome to the second section of Chapter 13, which is going to build on vector-valued functions. So in the first video, we learned what is a vector function, we talked about how to graph vector functions, and we looked at limits and continuity. Now we're going to build on that in this video, and we're going to talk about derivatives and integrals of vector functions. And we're going to start out with the definition of the derivative of a vector function. So that's what we see here. If R is some vector function, then the derivative of that vector function with respect to t, first of all, this is notation. So r prime of t, dr dt, and those should be pretty similar. And then here is your limit. Limit as h approaches 0 of r of t plus h, subtract r of h over h. There's a quick typo here. I want to fix this should be a t, not an h. Okay, so this should look pretty similar to definitions of derivatives that you've talked about in the past. Before we actually use that definition, we're going to talk about geometrically what this means. So let's say that we have some vector function in 2 space, like this. We have r of t, which is some vector that ends at that point. And then we're going to add h onto that, which is going to give us a different point. So this is r of t plus h. So then if we connect those 2 points, this vector here is going to be the vector that describes r of t subtract r of t plus h, or really the other way. And this is the secant vector. Okay, so then what we're talking about in this definition is we want h to become really, really, really small. So if h becomes really, really, really small, we're going to end up with a vector that is much closer to our initial vector. So here was our initial vector. Here was our r of t plus h. And then we had our secant that we drew in. Okay, so if we pick something significantly closer, we're going to end up with a more accurate secant line, and ultimately what we are looking for, that wasn't great. Ultimately what we are looking for is the tangent line. Okay, so here's what's important. That r prime of t is a vector that is tangent to the curve at the tip of r of t. And also what is very important is that it points in the direction of increasing parameter. So right about now, you're probably asking yourself, am I always going to have to use that definition? Because I didn't like doing it in Calc BC and I don't want to have to keep doing it. And the answer is no. We're going to look at this theorem. So if you have some vector-valued function in 3 space or 2 space, and those individual functions are differentiable, then when you find the derivative of r of t, you can do that by just taking the derivative of each individual function. Now, you shouldn't just trust me because I'm telling you that. You should want to know, why is that the case? So of course, let's look at a proof. Okay, we are going to prove for 2 space. The proof for 3 space is going to be a similar idea. So I'm going to say let r of t be equal to x of t, y of t. By definition, r prime of t then is going to be the limit as h approaches 0. And we're going to do the limit. I'm going to start by just writing the definition. So this is going to be r of t plus h, subtract r of t over h, which in our case is the limit as h approaches 0. Okay, so r of t plus h is x of t plus hi, add y of t plus hj, subtracting r of t, so that's going to be x of ti, add y of t day, over h. So that's the definition. Now is a good time to pause and make sure we're going to get to where we need to get to. Where we need to get to is that to find the derivative, we can just take the individual derivatives of the functions. So I'm going to need to separate this. So I have my first component together, my x component together, and then my y component together. So this is going to be equal to the limit as h approaches 0 of x of t plus hi, subtract x of ti over h, plus the limit as h approaches 0 of y of t j, subtract y of t plus h, j, subtract y of tj over h. And that is the limit as h approaches 0 of x of t plus h, subtract x of t over h, all of that I, plus the limit as h approaches 0 of y of t plus h, subtract y of t, all over h, j, which gives us then x prime of ti plus y prime of tj. Okay, so what did we prove? We proved if you're finding the derivative of a vector function, you can find the derivative of the individual functions. And remember, to show that our proof is done, we either write QED or write a little box that we fill in. Okay, so let's see this in use. Example 1, we have r of t, and we are finding r prime of t. Okay, so our individual functions are 1 over t, e to the 2t, and negative 2 cosine of pi t. So then, our r prime of t, 1 over t, remember that's t to the negative 1, so I'm going to get negative 1 over t squared, and then I'm going to get 2e to the 2t, and then I'm going to get 2 pi sine of pi t. So there we go. Okay, so let's move on, or let's add on a little bit to the vocabulary. R prime of t refers to what we call the tangent vector. The tangent line, then, is the line that is through P, through some point, and that is parallel to our tangent vector. And one that you're going to see a lot is what is called the unit tangent vector. It's always denoted with a capital T. So we're going to take that tangent vector, but in order to make it a unit vector, so to have a length of 1, we're going to have to divide by the magnitude. Okay, so in the next example, based off of the previous example, we're going to find the unit tangent vector for example number 1 at t equals 1. So we are looking for t of 1. Well, we know our tangent vector that we already found is negative 1 over t squared, 2e to the 2t, and then 2 pi sine of pi t. So if we substitute 1 in then, we're going to get negative 1 2e squared and 0. We want this to be a unit vector though. Notation-wise, this should be a 1. So we are looking for r of 1, or the magnitude. So this is a square root of 1, add 4e to the 4th. So our unit tangent vector then at 1 is negative 1 over the square root of 1 plus 4e to the 4th. And then 2e squared over that square root, and then 0. And if you want to know what that is approximately, it's approximately negative 0.068, comma 0.998, comma 0. Okay, so this is a pretty beefy section. We have a bunch more examples that we're going to look at of how to apply this idea of the derivative. Okay, so let's keep going and let's look at an example where we're going to do some sketching. We have the curve r of t is equal to root ti plus 2 minus tj. First, we're going to find the derivative, and then we're going to sketch both r of 1 and r prime of 1. Okay, first thing that I want to do for the sketching part is I want to draw what this r of t actually looks like. So this r of t, if we make ourselves a little table where we are looking at t, x, and y, I'm just going to do 0, 1, and 2. And if I do that, I'm going to get 0, 2, 1, 1, and root 2, 0. 0, 2 is up here, 1, 1 is up here, root 2, 0 is here. And so it is this curve. Okay, so r of 1 is the vector where t is 1 and it ends at that terminal point. So this is our vector r of 1. Okay, and so now let's continue by finding the derivative. Derivative of root t is 1 over 2 root t. Derivative of 2 minus t is negative 1. So r prime of 1 then is 1/2, comma negative 1. Okay, so to sketch this, if we start at the origin, we're going to go x value of 1/2, y value of negative 1. So that's here. But what I really want is I want that from this terminal point right here. So I'm going to draw the parallel vector. So this blue one is our r prime of 1. And what I want us to notice in the figure is that we have r of 1, and then we have the derivative of 1 at 1, which is going to give us the tangent line. So that should be pretty satisfying. Talking about tangent lines, next example, we're going to look at writing the equation of a tangent line. Okay, we're going to find parametric equations for the tangent line to the helix that has equations at the point 2 cosine of t, sine of t, and z equals t. So here we go. We are going to find parametric equations for the tangent line to the helix that has those equations at the point 0, 1, pi over 2. I'm going to start then by writing this as one vector valued function. So it's going to be cosine of t, sine of t, and t. Tangent line means that we're going to need the derivative. Sorry, this is 2 cosine of t. So the derivative is going to give me negative 2 sine of t, cosine of t, 1. Okay, so now the question, though, is what value am I plugging in for t? Because I'm looking for the tangent line at a specific point, at this point right here. So that's great, but I'm going to need to be able to plug in some value of t so that I can find the vector that I need, the tangent vector that I need. Well, if we use that point to substitute into our equations, we get 0 equals 2 cosine of t, we get 1 is equal to sine of t, and we get pi over 2 is equal to t. So this is just x, y, and z. So that shows us we're going to use a t of pi over 2. So we want to evaluate r prime at pi over 2. And we're going to get negative 2, 0, 1. So this is our tangent vector. So then, if we want to write a vector equation of our line, we're going to get r of t is equal to, I'm going to use my point and my tangent vector. So I'm going to get 0, 0, 1, pi over 2 plus t times negative 2, 0, 1. So parametrically then that gives me x is equal to negative 2t, y is equal to 1, and z is equal to pi over 2 plus t. Okay, so now that we've had some practice with finding the derivative and what does it mean, how to calculate it, we are going to look at some rules, some differentiation rules that'll hopefully be helpful to us. So here are all of your rules. Many of them are going to be fairly intuitive. If you're adding two vector functions and you're taking the derivative, you can take the derivative separately. If you're multiplying by some constant, you can pull it out. Here is where things get more interesting. If we have some function, this is just a regular function multiplied by a vector function, we're going to do the product rule. Okay, then looking at dot product. It's going to be similar to the product rule. I'm going to take the derivative of u and keep v, then I'm going to take the derivative of v and keep u. Cross product. Similar idea, but we need to pay attention with order. It's always going to be uv. And you should be asking yourself or trying to think, why does that matter? Well, dot product, remember, just is going to give us a number. So if we dot two vectors, a dot b is exactly the same as b dot a. So it doesn't matter the order that I take the dot product in. Cross product, though, is going to give us a vector. A cross b is not the same as b cross a. If we cross in a different order, we're going to end up with the opposite sign vector. So you need to remember, always do u first. And then we do have a chain rule. Okay, so let's go on and see how these are going to look. Moving on with a theorem, if r of t is differentiable and the magnitude of r of t is constant for all of t, then r dotted with r prime is going to be 0. Okay, so why do we care? Well, if a dot product equals 0, that means that our vectors are orthogonal. But they're orthogonal for all t. Okay, so let's just do a whole bunch of examples to see what this is going to look like. So example 4, the graphs of r1 of t and r2 of t intersect at the origin. Find the degree measure of the acute angles between the tangent lines to the graph of r1 and r2 at the origin. Okay, so r1 of t, in this case, is going to be inverse tangent of t, sine of t, and t squared. r2 of t is going to be t squared subtract t, 2t minus 2, and natural log of t. Okay, so we're going to find the degree measure of the acute angle between the tangent lines at the origin. Okay, so first thing is, it is very intuitive to jump in and think the origin happens at t equals 0 for both of these. And that's not the case. So the first thing we have to figure out is, when do these graphs actually hit the origin? So when is r1 of t equal to 0, 0, 0? Well, that happens at t equals 0. So it actually happens at t equals 0. But for r2 of t, so when is r2 of t equal to 0, 0, 0? Well, hopefully we can see, particularly from that natural log of t, that this happens at t equals 1. So we're going to be operating with two different t values. Moving forward, if we're looking at tangent lines, then we're going to need the derivative. So the derivative of our first vector valued function, do we remember the derivative of inverse tangent? Maybe, maybe not. It's 1 over 1 plus t squared. And then we get cosine of t and 2t. For our 2 of t, we get 2t subtract 1, 2, and 1 over t. Okay, so this is a good point for us to pause and make sure we have a direction moving forward. We are looking for the acute angle between the tangent lines. Okay, so we're going to next have to find, this is a prime, we're going to have to find what the derivative is at 0 for our first vector function, which gives us 1, 1, 0. And then what the derivative is at 1 for our second function, because that's when we hit the origin, and we get 1, 2, 1. So now if we want the angle between them, we are going to have to dot our vectors, divide by their magnitudes, which gives us root 3 over 2. How convenient. So our angle is pi over 6, or 30 degrees. Okay, so let's move on. Next one, we are going to be finding the derivative of a dot product and a cross product. So we are going to do this directly and then using the formulas. So when I say directly, I mean find the dot product, then do the derivative. So let's start with our dot product. So I'm going to start by finding the dot product of R1 and R2. So that is the dot of 2t, 3t squared, t to the third, dotted with 0, 0, and t to the fourth, which is very convenient. It just gives us plain old t to the seventh. So then if I want to take the derivative of that dot product, I'm going to get 7t to the sixth. Okay, so now if I use the formula, I'm going to take the derivative of R1, dot it with R2. I'm going to add to that R1 dotted with the derivative of R2. So the derivative of R1 is 2, 6t, 3t squared, and I'm going to dot that with 0, 0, t to the fourth. And to that, I'm going to add 2t, 3t squared, t to the third, dotted with 0, 0, 4t to the third. And that is going to give me 3t to the sixth, add 4t to the sixth, which is 7t to the sixth. Now, that should not be a surprise. Of course, if we take the derivative directly or we use the formula, we should get the same answer. It's not always going to be that one is faster than the other, but hopefully we can see that in this case, directly was faster. Now, let's take a look at the cross product. If we do it directly, we're going to have to start by finding the cross product of these two vectors. So we're going to get I, j, k, 2t, 3t squared, t to the third, 0, 0, t to the fourth. So this is going to give us 3t to the sixth subtract 0, and then negative 2t to the fifth subtract 0, and then 0. So that simplifies to 3t to the 6th, negative 2t to the 5th, 0. And so now if I take the derivative of that, I'm going to get 18t to the 5th, negative 10t to the 4th, and 0. So that was directly. And now we're going to look at using the formula. Okay, so if we use the formula, remember order matters. We're going to take the derivative of r1 and cross it with r2. And then we're going to take r1 and cross it with the derivative of r2. So this will be j, k, 2t, 3t squared, t to the 3rd, and 0, 0, 4t to the 3rd. And then we're going to take the second cross product. And we have 2, 6t, 3t squared, 0, 0, t to the 4th. Interest of time, we're not actually going to do that. But I will tell you, shocker, I know, you're going to get the same answer. So either way works. You need to know both how to do it directly and using the formula. But you can choose whichever way you prefer. Okay, you guys have stuck with me for quite a while. We have a few last examples to do, or a few last things to talk about. Now that we have derivatives down, we need to look at integrals. Okay, so if we're taking the integral from a to b of some vector function, here's our definition on the right. So this is the integral using Riemann sums. If you remember this, you're going to split up into rectangles. You can choose any t value that you want in each rectangle, so on and so forth. Realistically, we're not going to use that. What we're going to do instead is we will integrate each individual function. So let's end this with a few examples. Okay, example 6. We have r of t, is the r of t we used at the beginning of the video. We are finding the definite integral from 0 to 1. So what that's going to look like, the integral from 0 to 1 of r of t dt. We're going to take the integral from 0 to 1 of t squared dt, and that's times I. Then we're going to have the integral from 0 to 1 of e to the t dt times j. And then we have the integral from 0 to 1 of negative 2 cosine of pi t dt, all of that times k. So this is then 1/3 t cubed from 0 to 1 I. This is e to the t from 0 to 1 j. And then this is negative 2 over pi sine of pi t from 0 to 1 k. So simplifying all of that, our final answer is going to end up being 1/3 I add e subtract 1 j. Okay, next example, example 7. What do we do if it's an indefinite integral, if we don't have bounds of integration? Well, we're still going to integrate our parts separately, and so we would get t squared I, and we're going to get t to the cubed j, but we have this vector c, this constant. So if you don't have limits of integration, you're going to have a constant c. Similar to what you had in BC, it's just going to be a vector. And then the last thing we have to do is be able to find that c. So, very last example for this video. Thank you for sticking with me. We're finding r of t given r prime of t and r of 1. So if we start by integrating r prime of t, then our r of t is going to be equal to 3t t squared add some c. Okay, so then here's what is important. We have this 2 comma 5. So we get 2, 5 is equal to 3, 1 plus, and I think it's more helpful to write that c in terms of its components, right? It has an x component and a y component. So then we get that c to be negative 1 comma 4. So finally our r is 3t subtract 1 and t squared add 4. So thank you for sticking with me on this video through derivatives and integrals of vector functions. It should have reminded you of a lot of pieces that you covered in Calc. The thing to be careful of, or where most people might make mistakes here, is with notation. So please make sure that you are careful with your notation, that you are showing that r is a vector, that you are showing that c is a vector, knowing between when something is a vector versus just a point, using your I and J notation or using your bracket notation. That's something that I will pay particular attention to. So hopefully this was clear. Good luck on your homework.